Hello everyone. Today we look at Chapter 1. So our first chapter in the statistics book is titled Getting the Information You Need. This chapter is a little bit unique because it's pretty much all terminology, just trying to get you more comfortable with some of the terms that you're going to be using throughout the remainder of this course. The chapter is organized into sections. Chapter 1, I believe, is organized into 6 sections. So you'll notice this is section 1.1, Introduction to the Practice of Statistics. You can look on the upper right-hand corner of every odd-numbered page in your book, and it'll tell you what section of the chapter you're on. We start out with the definition of statistics. It's the science of collecting, organizing, summarizing, and analyzing information to draw conclusions or answer questions. In addition, statistics is about providing a measure of confidence in any conclusions. I think one of the reasons that I'm so fond of statistics and teaching statistics is because there are so many overlapping things with this and my other area of study, which was accounting. The definitions are quite similar. Both look at precision and confidence in your numbers. We start out with data. So we hear about this all the time. We look at the data of a study, the data given for some type of experiment or survey or something like that. Data are a fact or proposition used to draw a conclusion or make a decision. The entire group of individuals or subjects being studied is called the population. An individual is a person or object that is a member of that population being studied. A sample is what we deal with a lot here. A sample is the subset of the population or the group of the population that's being studied. We'll talk a lot throughout this course about samples and how that sample relates to the population. We look at descriptive versus inferential statistics. Descriptive statistics describes data. A good example, 25% of M&Ms from a given bag are red. From that, I can use inferential statistics to apply those results and look at a sample and see if from the sample to the population, if I can verify those numbers. So if I had 100 bags of M&Ms, would that percentage of red M&Ms still be 25%? That's what inferential statistics could tell me. A parameter is a numerical summary of a population. Think about surveying everyone in the class about eye color. The results are considered a parameter because you ask everyone. The results of the U.S. Census are considered a parameter. Many people today very loosely consider the U.S. Census a parameter. There's a lot of skepticism that many groups of individuals in the United States are omitted from census data because they have no way of being tracked. There's an example later in the chapter that discusses this. Now let's go back to the eye color of everyone in your class. Say you did a survey of your entire school. You chose a sample, and that sample asked maybe 150 out of the 1,000 students at your school what their eye color is. That's not considered a parameter because every single person wasn't being asked. That was just more of a general statistic. The chapter looks at qualitative versus quantitative. So in statistics, a big thing is qualitative versus quantitative. How will we do our study? What type of study will it be? What kind of variables are we using? And that's where qualitative versus quantitative come in. I always thought about it starting from the approach of quantitative. When you hear quantitative, you probably think of numbers, and that's what quantitative variables are. They're numerical. They can be counted. Qualitative, I always think about as, say, the quality of a survey, the quality of people's opinions. Qualitative data is more about what people are doing or what they're thinking or how they feel. Many studies, and for example, my dissertation study was a case study here at the college on retention over the past decade. It had qualitative and quantitative elements to it. It was a mixed methods study. Then we break that down in the quantitative area between discrete versus continuous variables. This can be a little bit confusing, but one thing I suggest, look up examples. Google it, discrete versus continuous variable examples. Discrete variables are exact or countable. Continuous is in a range. So an example for discrete could be the year you were born. For continuous, it could be the temperature. Now, for both of these, the year you were born is discrete. You were born in a certain year. You were born in 1980, or in 1992, or in 1954. It's just asking the year you were born. If it said the exact time you were born, that would be continuous, because it would be looking at you're so many years old, so many years, so many months, so many weeks, so many days, so many minutes, so many seconds, and that's continually changing. With temperature, that's a continuous scale too, because the temperature is fluctuating. It's on a seemingly never-ending scale in both directions, above and below zero. You know, it could be 92.85 degrees or 856 degrees, or I mean, it can vary. So it's more like a sliding scale. The next part of section 1.1 looks at levels of measurement, and this wraps up this first section. So we go in 4 levels: nominal, ordinal, interval, and ratio. Each one builds on the other. Nominal is the most basic. Words, letters, symbols. On a survey, it could, when it says, what's your gender? Male or female. You choose, that's nominal. Ordinal can be ranked. So possibly grade distributions. Maybe grades that you got on an exam. So if I look at all of the grades that my students get on an exam, that's grade distribution. Or a Likert scale. How much did you enjoy this movie on a scale of 1 to 5? That's ordinal. It can be ranked. Interval goes one step further, so it combines nominal and ordinal, and it adds that it can be ranked and ordered. So temperature differences in dollar amounts. It's saying the incremental change in temperature, for example, from 75 to 76 is the same as the incremental change from 88 to 89, or 115 to 116. Same thing with dollar amounts. It's the same interval amount between $1 and $2, or $115 and $116. And then we have, finally, the ratio level of measurement. This has an absolute 0. Now, something that's highly discussed and very, very confusing for many students to see is why temperatures are interval. And people say, well, a temperature does have an absolute 0. If you think about the temperature, it goes from 0 up to, and basically it could be an infinite amount. It also doesn't stop at 0, though. It goes below 0. We have sub-zero or negative temperatures. So there isn't an absolute 0. A good example of an absolute 0 could be money in your pocket at any given point, or in your wallet. You could have $20, you could have $58.25, you could have no money. You'd have $0. That has an absolute 0. Now we start section 1.2, observational studies versus designed experiments. An observational study, and you can read the definition here, but basically this is where we are observing something without influencing it. Observational studies are a very common type of study to do. It says if a researcher assigns individuals in a study to a certain group, intentionally changes the value of the explanatory variable, and then records the value of the response variable for each group, the researcher is conducting a designed experiment. It gives a good example in the book about confounding and lurking variables. So they talk about in the book about looking at senior citizens and what proportions of them got the flu shot. So it asks two different things. About the proportion of them that had the flu shot compared to how many were hospitalized with the flu, and about the proportion of them that got the flu shot and how many of them died from the flu. That brought in several lurking variables. Basically, things about pre-existing things with the people in the study, their age, their health status, or their mobility. Those are just things that a lot of times when you're looking at overlapping things, and here we're looking at two different things. How many were hospitalized and how many died. So basically, one thing that the book looks at as a major point is, and this is listed on page 16 in your book, observational studies do not allow a researcher to claim causation, only association. Through an observation study, you can say there's an association between things when you find a positive correlation between them, but you cannot say that one thing absolutely causes the other. Section 1.3 looks at simple random sampling. So this is a pretty short and sweet section. Random sampling is very important in statistics. It's the process of using chance to select individuals from a population to be included in the sample. So a sample size of n, lowercase n, from a population of size n, capital N, is obtained through simple random sampling if every possible sample of size lowercase n has an equally likely chance of occurring. The sample is then called a simple random sample. We want to make sure when we're studying a sample that that sample is representative of the population. We don't want to skew our study by handpicking every specific person for a certain reason. We want to make sure that we have a nice random sample to work with that still does give a good representation of the population. Section 1.4 just looks at other effective sampling methods. A stratified sample is obtained by separating the population into non-overlapping groups called strata, and then obtaining a simple random sample from each stratum. So the individuals within each stratum should be homogeneous or similar in some way. That's one type of sample. A systematic sample is obtained by selecting every kth individual from the population. The first individual selected is a random number between 1 and k. You see systematic samples of people chosen a lot of times at stores when every, say, 100th customer wins a prize. A cluster sample is obtained by selecting all individuals within a randomly selected collection or group of individuals. And then a convenience sample is one in which individuals in the sample are easily obtained. You have to be really careful with a convenience sample. I would suggest that this is never chosen as the method to choose your sample, if at all possible to choose something else. It doesn't give a very faithful representation. People will question convenience samples. Section 1.5 looks at bias in sampling. If the results of the sample aren't representative of the population, the sample is said to have bias. 3 sources of sampling that we'll look at on the next slide are sampling bias, non-response bias, and response bias. We'll look at all 3 of these. We start with sampling bias. That means the technique used to obtain the individuals to be in the sample tend to favor one part of the population over another. Undercoverage results in sampling bias, and undercoverage occurs when the proportion of one segment of the population is lower in a sample than it is in the population. Non-response bias exists when individuals selected to be in the sample don't respond to the survey, have different opinions from those who do. Non-response can be improved through the use of callbacks or rewards and incentives. Response bias exists when the answers on a survey do not reflect the true feelings of the respondent. Types of response bias: one could be interviewer error, so something the interviewer does mistakenly to skew the responder's answer. Misrepresented answers. The way questions are worded can cause response bias, and the order of how questions are asked. The order is a big thing because it's very easy to order your questions in a way that skews what your results are going to be. It can almost make them leading and influence people to answer a certain way. You never want to do that. Data entry error is another bias in sampling, and that's simply someone inputting information incorrectly. Non-sampling errors are errors that result from sampling bias, non-response bias, response bias, or data entry error. It says such errors could also be present in a complete census of the population. And again, that goes back to early in the chapter where I talked about the U.S. Census being a parameter. There's a great many people and groups in the United States that think we miss a huge component because it's impossible to think that the U.S. Census Bureau is going to be able to track down every homeless person to give their documentation and information to for a census count. Sampling error is an error that results from using a sample to estimate information about a population. This type of error occurs because a sample gives incomplete information about a population. Section 1.6, the final section of this chapter, looks at the design of experiments. So an experiment is a controlled study conducted to determine the effect of varying one or more explanatory variables or factors has on a response variable. Any combination of the values of the factors is called a treatment. The experimental unit or subject is a person, object, or some other well-defined item upon which a treatment's applied. A control group serves as a baseline treatment that can be used to compare to other groups, and a placebo is an innocuous medication, such as a sugar tablet, that looks, tastes, and smells like the experimental medication. They do that a lot in the pharmaceutical field, as you can tell from this example. Blinding refers to non-disclosure of the treatment and experimental unit is receiving. A single blind experiment is one in which the experimental unit or subject does not know which treatment he or she is receiving. Where a double blind, neither the experimental unit nor the researcher in contact with the experimental unit know which treatment the experimental unit is receiving. So this gives a good overview of some of the terminology from the chapter. And then each week we'll be doing the active learning lecture slides in class. So I'll record this right here on the tail end of the class lecture PowerPoint for those of you in the alternative format class. So for Chapter 1, we are going to start out with a question that says, a survey of 200 adults in the U.S. found that 76% regularly wear seatbelts while driving. True or false? 76% is a parameter. So I'll give you a second. So the correct answer is false. It's a survey of 200 adults. That survey was looking at a sample of 200 adults. They did not survey every single adult in the U.S. So that's a statistic, not a parameter. True or false? The checking account numbers of customers at a bank represent quantitative data. And that one's false. This one can be a little bit tricky, but we're not asking about dollar amount balances in the accounts or anything like that. These are the checking account numbers. While it is numeric data, that numeric data doesn't represent anything except the identifying information for that customer. Account numbers are many times just a jumbled selection of so many digits. They don't distinguish the actual data in any way. So next is determine whether the quantitative variable is continuous or discrete. The time in minutes required for a student to complete a quiz. So think about this one. It doesn't say the exact time someone completes a quiz. It wants to know the time in minutes required to complete a quiz. That's continuous. That could be somebody took 8 minutes and 58 seconds, and somebody took 9 minutes and 12 seconds, and somebody took 10 minutes and 1 second. It's on that continuous scale. Identify the variable's level of measurement. Consumer Reports ratings. Best Buy, recommended, not recommended. Okay. So Consumer Reports ratings for Best Buy, recommended, not recommended. And that's going to be ordinal. So it does list like nominal data, but it can be ranked whether something is recommended or not recommended. Determine whether the study depicts an observational study or an experiment. Two sections of statistics are taught by the same teacher. One section uses MyStatLab, the other section does not. At the end of the semester, grades in the two sections are compared. So is this an observational study or an experiment? And this is an experiment. We're not so much just observing the two sections. This is a more controlled one section using MyStatLab, one not, and then at the end seeing how that affects the grades. Identify the type of sampling used. Students at a university are classified according to major. The administration randomly selects 5 majors. All students majoring in those 5 areas are surveyed. So that's a cluster sample. The university has randomly selected 5 majors, so those are kind of your clusters. All students in those majors are sampled or surveyed. So that's a cluster sample where you're surveying or questioning all the majors in those 5 different areas. Determine the type of sampling bias. A college wants to survey students about reducing the hours of the computer lab. To conduct the survey, they select the next 50 students to enter the computer lab. So this would look at sampling bias. This should show you a little bit more about that convenience sample. We just are taking conveniently the next 50 students to come into the computer lab. This could really skew our data because those 50 students could all be in the same class and have a time crunch on getting a paper done. So that could skew our data and cause bias. So then finally, determine the type of experimental design. A company wants to study the relationship between product placement on a shelf and sales volume. 20 stores of comparable sizes are selected and 5 stores are randomly assigned to each of the 4 shelf levels. After a month, the sales volumes of each group are compared. Okay, and these types of samplings were discussed in section 1.6 near the end of the chapter. This is called a completely randomized design. So 20 stores of comparable size are selected. 5 stores are randomly assigned to each of the 4 shelf levels. So that's a completely randomized design. All right, so that wraps up chapter 1. If you have any questions on the chapter or anything else, please feel free to let me know. Thank you.